Hello, and welcome to the homework tips video for homework 2 from Astronomy 10. Okay, so in this homework, we have two problems, and they're both very directly related to angular size. So really, honestly speaking, there's just one equation you're going to use, and you just have to use it over and over again and make some conversions. So of course, let's talk about that one equation that you're going to use, why we're going to use it, because there actually are alternate versions of it based on different approximations, but I want you to use one particular simple version, and then just some tips about how to do the particular problems. So let's start by reading number one. So we're told that the moon's precise equatorial diameter, so that's just how big the moon is, right, how wide across, is 3,476 kilometers. And its orbital distance, all right, so there's an important number right there. Let's go ahead and underline that. And its orbital distance from Earth varies, okay? It varies between 356,400 and 406,700 kilometers. So that's its closest at the 356 and furthest distance at the almost 407, okay? In terms of hundreds of thousands of kilometers. Meanwhile, we've got the sun's diameter. Again, we could assume this is, somewhat precise, but we have less significant figures. So you're really working with 3, by the way. Right, so there is the sun's diameter, much bigger than the moon, of course, vastly larger than the moon. But it's also much further away. Instead of being a distance of a few 100,000 kilometers, the distance from the Earth to the sun varies between, at closest approach, 147.5 million kilometers to furthest at 152.6 million kilometers. Okay, so orders of magnitude greater. All right. And then we're asked to find the moon's angular size at its minimum and maximum. Okay, so it's a good starting point there. And finally, I'm going to segue to that one key equation that I hinted at a moment ago. Okay, so again, this equation, you're using all parts of both problems, 1 and 2. Okay, so what is that equation? Well, it's the equation for angular size. So we'll call this the angular size equation. Okay, because angular size is measured in radians, okay? Okay, we'll point that out. So angular size, not degrees, at least not in the equation that I'm going to give you. Now you could easily convert from degrees back to radians, but we don't need to in this problem, so let's not talk about it, okay? You can look that up on your own if you're interested. Angular size is measured in radians, okay? And the statement says that theta, okay, which is angular size, is going to be equal to distance over diameter. All right, so R over D. All right, let's go ahead and label our variables here. All right, so theta is angular size in radians. All right, R is the size of the object. So this is actual size of object. In what units? Well, if we're using the real base unit of astronomy, it should be meters, but in practical sense, we can do it in kilometers. We want to make sure, in fact, we have to make sure that we stick with kilometers. All right, so R is actual size of object in kilometers, km. Meanwhile, distance must also be measured in kilometers, and it's the distance. Okay, so distance to object, so it's how far away it is from you, the observer, in kilometers. So again, I'm using kilometers both times. That's so important because I need those kilometers to cancel out up here so that I have no remaining units, because radians don't have units, okay? They're unitless, okay? All right. So that's the one equation we're going to use each time. So if we take a look at what I'm asking for in part A, where I say find the moon's angular size at its minimum and maximum distances, you're going to be finding its maximum and minimum angular size. In that order, by the way. Because when the moon is at its minimum distance, that's when it's closest to Earth, well, it's going to be the biggest size, right? Which of course makes sense in this equation because that's when D is smallest. When you're dividing by a smaller number, a smaller distance, you're going to get a larger angular size, which also makes intuitive sense because when something is closer to you, it appears bigger, which is to say it has a larger angular size, because that apparent size is what angular size is. It's how much of your vision that object takes up, in a sense, okay? So you're going to calculate those two numbers in part A. Simply report what they are, label them appropriately, okay? And again, using this formula, all right? And it's of course going to be the same moon, so you're going to use the same R both times. Then in part B, what is the maximum variation of the moon's angular size? Okay, so for part B, you're simply going to take the difference between the maximum angular size and the minimum angular size. Okay, so let's make a note of that. So in 2A, just use theta max equals R over D min, for example, okay? And use something very similar, of course, for theta min. And then for B, you're just going to find the difference, which we call delta theta, because delta always represents the difference, and that's just going to be theta max minus theta min, okay? Then what about in part C? Because we're leading up to something, okay? Now, please excuse the formatting error here. It's not supposed to be a copyright symbol. It's supposed to be C. But find the sun's angular size at its minimum and maximum distances from Earth, okay? So again, same sort of thing. You're going to find its maximum angular size when it's closest to Earth and its minimum angular size when it's furthest from Earth, okay? So same idea there, for example, right? But you just plug in the numbers appropriate to the sun, okay? And then you're not going to be asked again for the variation, but you have a follow-up question here, E. The most interesting part of number 1, I would say. Based on your answers to parts A and C, you don't really need part B to answer this, but based on the values that you got in A and C, is it possible to have a total solar eclipse when the moon and sun are both at their maximum distance? Okay, so it's so important about part D, because again, part C is just like part A, but for the sun. But what's so important about part D is you need to conceptually think about what is necessary for a total solar eclipse. For a total solar eclipse, okay, so condition for total solar eclipse is that the angular size of the moon and the sun are equal to each other, yes, but specifically that the moon is either equal to the angular size of the sun or greater than, okay? So we need the angular size of the moon to be equal to or greater than the angular size of the sun. Because if the angular size of the moon is even a little bit less than the angular size of the sun, it won't completely cover the sun during a solar eclipse. If it doesn't completely cover the sun, that is not a total solar eclipse. There's a name for that, and it's called an annular solar eclipse, but it's not a total solar eclipse, okay? But you need to show numerically that that's possible for the moon to have an angular size smaller than that of the sun, okay? And you have to show that numerically, refer back to the values that you have from parts A and C, and clearly refer to those values in part D so that I know you have the right numbers and you're using them appropriately, okay? All right, so that's it for number 1. Number 2, I asked you to estimate the diameter of the supergiant star Betelgeuse, okay, which is one of the biggest stars that is near our sun, right, in our section of the Milky Way, using its angular diameter of about 0.05 arc seconds and distance of about 600 light years. Okay, so what's going on here? Well, here you do have to make the conversion that I wasn't getting into before, which is to say converting from arc seconds into radians, okay? So one key thing about number 3, and let me resize it a bit so I can put a couple notes down here about number 3. So one key thing about number 3 is you have to convert arc seconds to radians, okay? And to do that, you need to first convert arc seconds into degrees. And there are 60 arc seconds in an arc minute, and there's 60 arc minutes in 1 degree, which is to say that 1 degree is equal to 3,600 arc seconds, okay? Furthermore, 1 degree is equal to some fraction of a radian, but it's not an easy one to think of or express that clearly. So what I always do is I always say that 180 degrees is equal to pi radians. Okay? So we'll say and, right? And this is one of our key conversion factors there. All right, leave it like that. And oh yeah, and 180 degrees, so half a circle, is equal to pi radians, because the full circle is 2 pi radians. Okay? So those are the two conversions that you need to convert from arc seconds into radians, okay? Because again, this equation only works in radians. So you have to do that conversion up front as a first step. Then you have to convert, of course, 600 light years into kilometers. That's a value that you know, at least in terms of 1 light year is so many kilometers. It's a value that's in the book. So certainly use that conversion. I won't give you the number here, but use that conversion to convert light years to kilometers. Once you have that, then you're going to be in a place where you can solve for the actual distance. All right, so compare your answer to the size. Oh no, you're going to solve for R, okay? Because you know D, okay? Because you've converted that 600 light years into kilometers, which gives you your value of D. You converted your 0.05, so a fraction of an arc second, into radians, which gave you your theta. And what are you going to solve for? You're going to solve for R. So in other words, the actual size of Betelgeuse is going to be R equals D theta. Okay, let's write that down there. R equals D theta. Okay, that's going to be the actual size of Betelgeuse. Now you can write that number, and in your work you should, but I ask you to compare your answer to the size of the sun and the Earth-Sun distance. So I want that comparison as a percentage, as a fraction. So, for example, this would be R for Betelgeuse, B for Betelgeuse. Maybe you could say that that's equal to 10 times the radius of the sun, because maybe it's 10 times bigger than the sun. And maybe that's also going to be equal to 1/100th of the distance from the sun to the Earth, SE for sun-Earth. So that's what I'm looking for, is some sort of fraction relationship. A percentage is also fine. You could say that it's 10% of the radius or something along those lines, okay? Or 10% of the orbital radius, that you need to make that comparison clearly in whatever way you see fit, okay? In part B, I say if Betelgeuse was instead as close to us as our closest neighboring star, Proxima Centauri, at 4.22 light years, then how large in arc seconds would Betelgeuse appear in the sky? So here, you're going to be solving for D. You're given D, but you're solving for theta. So you're actually going to be doing the same thing as you did in number 1. You have an R, right, which you found in part A, the actual size of Betelgeuse. You have a hypothetical new distance, okay, not the actual distance of 600 light years, but a new distance of 4.22 light years. You're going to put in that hypothetical distance for D and then solve for an angular size for Betelgeuse. That's what you're doing in part B of number 2. Now, that when you solve for that angular size using this formula, it's going to give you an answer in, yep, radians, but I want that answer in arc seconds because I want to compare back to the actual angular size of Betelgeuse, which is expressed in arc seconds. So that's why you want to convert back to arc seconds, and that's the one answer you're going to give to number 2, part B, is a value in arc seconds. Okay, so hopefully all these steps make some sense, and this tip video has been helpful. All right, bye for now.